Hi, welcome to Dissolved Chemistry. In the previous video of thermodynamics, we have discussed regarding expansion work. Let us briefly revive. There are different types of work. Say for example, you can take expansion work and non-expansion work. We categorize works into expansion work and non-expansion work. The work which involves change in volume. Okay, so that we call it as what? Expansion work. And other works. All other works are called non-expansion work, like electrical work. Okay, or you can take extension work. Right, etc. we can say. So this change in volume already in the previous class we have discussed, and it is a matter of our thermodynamics where we are supposed to discuss or work is equal to minus P external into delta V. So that is what we have derived. Okay. So in today's class we will see different types of these expansion works. What do you mean by free expansion? Well, prior to going for that particular, we will see a general example. Suppose you want to play a match, okay, and the opposite team has declared without playing the match, and then you will be decided as a winner. So there, have you done any work? No. So similarly, so work definition itself says that acting or moving against an external force. When there is no external force, okay, so there is no opposing force means what? So you will means the work done will be what? Zero. Opposing force is not there means it will be zero. So therefore, free expansion means expansion in vacuum is called free expansion. So expansion in vacuum means you don't have any external opposing force, as we found in the case of in deriving expansion work. P external was the opposing force, okay, over the area of the piston. Now what we see is this P external is zero, because it is in a vacuum, where when there is a vacuum then there is no force at all. So therefore work done will be is equal to zero when it is undergoing free expansion. Expansion in vacuum is called free expansion, where opposing force will be zero. Opposing force is zero. So therefore if you take the general work definition, that is 0 into area into dz, the overall will be 0. So that is called free expansion. Okay. Then second type we will see that expansion at constant pressure. At constant pressure. Okay, when the external pressure is maintained constant, the expansion is due to whatever the change happens in the system, okay, against a constant pressure. Say for example, you take a system, right, containing a gas fitted with weightless frictionless piston, and you are having certain, or the P external is nothing but atmospheric pressure or pressure of the surrounding, we can say, and which is always constant, and whatever the change is taking place, that is all taking place within the system, and that leads to what? Means your opposing force is constant now. So when opposing force is constant and driving force is also constant means what? Both are same means what? So there is no net work. So as the internal pressure develops, that will act as a what? Driving force for to lift this piston against a constant pressure. So therefore, say for example, you are doing some chemical reaction, as previously we have seen in the case of calcium carbonate decomposition. So similarly, any gas is evolved in this, and that gas is capable of doing work, because so it leads to increase in the pressure of the system, and it will drive this piston up against an external constant pressure. Then work is given as, okay, minus P external. The minus sign indicates we are working against an external pressure or external force, we call, right, into V initial, V final, delta V. Okay, if the difference is too large, we can write like this, minus P external into delta V. Okay, so your pressure is constant, and graphically we can represent this as the work done at constant pressure is, so we will show like this. Now suppose you imagine a cylinder here, okay, it is packed with a gas, and now its initial position is here, okay, and this is your initial, what you call, volume, V initial we call, right. Anyhow your pressure is going to remain constant. This is volume axis and this is pressure axis. So your P external, our pressure is constant. Now the change in volume occurs due to what? Change in the driving force, that is your pressure of the system. So now what happens? Your gas will expand from V initial to V final, means up to here it is going to expand, or you can take up to this, okay, like this. Fine. So that we call it as what? V final. Throughout your process, expansion work, your pressure is remaining constant. So therefore it is written like this, and your volume is, okay, and this is how we represent the work done by the system, okay, at constant pressure. The area under this curve, okay, the shaded area represents the work done by the gas. This is how we are going to represent, okay. So here work done will be is equal to P into delta V. So that is what is V initial, V final minus V initial, okay. So there is a gas which is going to expand, right. So from volume, this is the initial volume, and now this is the total final volume. So therefore W is equal to, at constant pressure, okay, so V final minus V initial, we write as W is equal to minus P external into delta V. Okay. So this is how we are going to represent the expansion work at a constant external pressure. Okay. Then next we will talk about, you make note of this, right. Then next is work done in reversible expansion. Okay, you should see here in the last case we have said that in the free expansion what I told is that there is no opposing force at all. Okay, F is equal to 0. So in this case what happens? External pressure, where at constant pressure what we have seen, external pressure is remaining constant. It is not going to change. Whatever the change which is happening within the system, that leads to the expansion of the gas. So therefore, say for example, any reaction which leads to the formation of gaseous products, so that leads to the expansion, or that will be the driving force which will lift the piston. Similarly, when we see in reversible expansion, how it is going to happen. Okay, reversible expansion work or work done in reversible expansion, you can write. Now the term, what do you mean by reversible, we have discussed very clearly. If you want, you can refer to our video, okay, on this particular topic. So therefore, here reversible meaning is what? Now if you consider a system, okay, so which is having an external pressure P external and some pressure inside the system, okay. So now when these two pressures are almost equal to each other, then that state we call it as what? There is a equilibrium state we call, or so both are when they are equal. If slight change if you bring on either side, then what happens? There is a slight movement or slight work done by the system we are going to observe. So as it is, the word is said in thermodynamics, reversible meaning is what? At any moment, if we change the variable, state variable, if the system can be altered on either direction, okay, either you can compress it or you can expand it by small infinitesimal change in the state variable, okay. So that we call it as what? Reversible meaning. Now say for example, P external is almost equal to internal pressure of the system. Now suppose here P external will not remain constant. Suppose slight infinitesimally it is being varied, okay, P external minus dP, small amount of the pressure, infinitesimal small change in the external pressure when it is being done. So then what happens? So that leads to, okay, lowering, small infinitesimal lowering of external pressure leads to slight expansion in the gas, okay, and so which is equal to P. So P external minus dP. So there, if we write work done will be what happens? A small change in the pressure P external minus dP, okay, so will lead to change in small change in the volume. When small change, infinitesimal change is brought in the external pressure, then slight expansion of the gas will occur, leading to the small change in the volume. Similarly, if you go on varying the pressure, why it so happens? At the same time, if you enhance the pressure little infinitesimally, if you raise external pressure, then what happens? Once again you can move back that one. That is nothing but a reversible case. So now similarly go on slightly varying the external pressure, then what happens? Step by step, in multiple step, slowly infinitesimal, slowly your system will do the work against external pressure, and that to get the total work done by the system, okay, we have to integrate this one, right, between the limits V initial and V final, P external minus dP, okay. So now what happens? Okay, into dV we will write. As the difference between these two is negligible, we can write as P is equal to minus P external is equal to P, already we have said, because it is a negligible difference we find, so therefore we can also write as dV, okay. So when the work is done, W reversible we write, and we will show like this, and graphically we are going to represent that. We will take same reversible work if you are doing at constant temperature, okay, so then it is called as what? Isothermal reversible expansion, okay. In that work done we will see that one, right. Third one is isothermal. This is what we are ending with for reversible expansion of the gas. Now further is isothermal reversible expansion of the gas. For that reason, what you have to do, so as we keep this integrals, okay, to integrate that, we have to change this pressure in terms of what? Volume. For ideal gas, P is equal to nRT by V. Okay, so now we know that when you maintain the temperature constant, right, then work done will be, so let us substitute that in this particular equation which we got for reversible expansion, that if you are doing in isothermal condition, then work done will be is equal to minus, okay, P, let us substitute, okay, we will write once dV. So therefore W is equal to minus nRT by V, okay, V initial, V final into dV. Okay, so now N is number of moles, R is gas constant, T is temperature. Anyhow, as it is isothermal, temperature remains constant. All three constants let us take out, minus nRT, okay, integration of V initial under the limits, V initial, V final, dV by V. Okay, so then we will get W is equal to minus nRT ln V2 by or Vf by Vi. Okay, or if you call this V initial as V1 and V final as V2, so then what it turns out to be, W is equal to minus nRT ln V2 by V1. Okay, so therefore we can calculate work done in isothermal reversible expansion by using this particular equation. Now suppose if it is given in terms of partial pressure, okay, then we know that for an ideal gas P1 V1 is equal to P2 V2. So therefore V2 by V1 is equal to P1 by P2. So therefore we can express the same equation in terms of what? W is equal to minus nRT ln P1 by P2. Okay, when the change in pressure, if it is given in the problems, we can use this particular equation. So now how we will represent this isothermal reversible expansion graphically, so that we will see. So graphically we are going to represent this work done in isothermal expansion of the reversible expansion of the gas is, say for example, this is your P initial pressure at the P external, that is initial pressure, okay, and this point you can consider as pressure final, and your gas is expanding, okay, we will consider the cylinder, right? So reversibly your gas is expanding, say this is the volume, initial volume, right, we call it as V initial or V1 we can call, right? Then what happens, slowly it is going to, as you go on decreasing the external pressure infinitesimally, a small change in the work we are going to observe. Okay, so then what happens, you will get like this, right? We'll take here small correction we will do. Okay, so initial, and this is the final pressure we call P final. So this is the pressure axis and this is volume, right? So V12, it will be going to change, say for example, V final here, right? So then so this is how your work done will be up to here. Okay, V initial, V final we call. Okay. So how this reversible expansion is happening? Every movement, right? So every movement there is a slight decrease in the external pressure leading to what? Expansion of the gas. Okay. So therefore what we will get? So we will get the curve like this, right? So this particular area under the curve will represent work done by the gas when it is expanding reversibly and isothermally. Okay, so this is what we call. So W is equal to minus nRT ln V2 by V1. Okay, so this is what is isothermal reversible expansion work. Okay, I hope you have understood. You should remember these equations and how to use and at what time we have to use. And in the next video, we will discuss regarding other aspects of the thermodynamics. Thank you for watching. Bye.